Ever stop to think about why a brilliant medical AI that works wonders in one hospital might just, well, completely fail when you try to use it in another?
Yeah, it's a pretty significant challenge, right? A real head scratcher.
We're seeing these incredibly powerful electronic health record foundation models being built, but what happens when they run into medical codes they've, you know, never encountered before?
It's a fundamental hurdle.
Yeah.
And that's exactly what a fascinating new research paper tackles head on.
Oh, okay. What's it called?
It's called MedRep, Medical Concept Representation for General Electronic Health Record Foundation Models. And it's all about making these AI models more adaptable, more generalizable.
Exactly. The paper really shines a light on this problem of unseen medical codes. Imagine this. Hospital A uses one system, say ISNO-MD-CT, to classify illnesses,
Uh-huh.
while Hospital B uses another, like ICD-10. An AI that's been trained on all of Hospital A's data might be totally lost when it sees Hospital B's codes.
It's like trying to decipher a completely foreign language, basically. The model just doesn't have the vocabulary.
Right.
And that's where the OMP Common Data Model, or CDM, comes into play. Now, for listeners who might not have heard of it,
Yeah, give us the quick version.
okay, so OMP CDM is a really smart initiative. It's all about taking this messy world of different hospital data systems and standardizing it, putting it into a single unified language, the OOP vocabulary.
A universal translator for medical codes.
Kind of, yeah. It can map over 9 million medical codes from all sorts of different systems. So the exciting promise is that if AI models are built using this OMP CDM,
They should just work everywhere that uses OMP.
they should, in theory, be able to work seamlessly across any hospital that adopts this standard.
Yeah, sounds like the perfect fix, doesn't it? Problem solved.
Well, here's where it gets really interesting. Even if hospitals are both using OMP CDM, actually combining their patient data is often a no-go.
Because of privacy regulations, right?
Yeah.
OP and all that.
Exactly. So these AI models often have to be trained separately, within each hospital's data silo. But get this, even hospitals that are both using OMP CDM might use different concept IDs for the exact same medical thing.
Wait, really? Even with the standard, how does that happen?
That's the core complication the paper tackles. They give a great example. Aspirin 100 mg oral tablet.
Oh, okay, pretty specific drug.
Right. But believe it or not, within the OMOP standard itself, that single concept can have multiple different concept IDs. They listed a few, like 111-3143, 4248-3115, and several others.
So 5 different codes for the same pill.
Potentially, yeah. Now, to an AI model just looking at the numbers, those look like completely unrelated things.
Even though they're essentially the same medication.
Wow. And this seriously limits how well these models can be applied generally, how they transfer.
It's like having, I don't know, a bunch of different product codes for the same can of soda at different supermarkets.
Yeah.
The main inventory system might not realize they're all the same thing.
That's a great analogy. And that's the central puzzle that MedRep is trying to solve. The goal is to help you, the user of these potential AI systems, get tools that are more broadly useful.
Okay, so our mission in this deep dive is clear. Figure out how MedRep aims to tackle this specific challenge, offering a path for these EHR foundation models to be more vocabulary agnostic, you could say.
Vocabulary agnostic, exactly. To work more effectively across different hospitals using OMP CDM despite these variations.
All right, let's get into it. How does MedRep actually work? You mentioned 2 parts.
That's right. At its heart, it's a 2-part strategy. First, there's something called concept representation learning, and second, there's trajectory augmentation.
Okay, break those down for us. Concept representation learning first.
Think of concept representation learning as giving the AI a much richer understanding of what each medical code truly means, going beyond just its specific ID number.
And trajectory augmentation.
That's more about making the AI more adaptable, more robust, to seeing slightly different sequences of these codes in patient histories, different journeys, if you like.
Got it. So let's unpack that first part. Concept representation learning. How do they give the AI a richer understanding?
Well, the researchers started by essentially beefing up the information linked to each concept ID. You know how standard OMOP concept names can be quite short and to the point.
Like our aspirin 100 milligram oral tablet example. Pretty basic.
Exactly. So MedRep uses large language models, LLMs, the same kind of tech behind things like ChatGPT, to generate much more detailed clinical descriptions for each of these concepts.
Using AI to explain the concepts to the AI.
Sort of, yeah. They focused on 4 main areas or domains within the OMOP CDM: conditions, drugs, measurements, and procedures.
The core types of medical events.
Right. And what's really clever is that they use different prompts, like tailored questions for the LLM for each of these areas to get really relevant explanations.
Can you give an example?
Sure. So if you have a concept like neutropenic fever, which is just a name,
Uh,
an LLM could expand on that. It might explain that it's a fever in patients with a low count of neutrophils, which are a type of white blood cell. It often happens because of chemotherapy. And crucially, the fever might be the only sign of a serious underlying infection.
okay, so much more context than just the name.
Way more context. This gives the AI a much deeper understanding of the concept, not just the label. It's teaching the AI the clinical context, how it relates to other things, moving beyond a simple dictionary lookup to, well, something closer to genuine understanding.
Right, so once they have these much richer descriptions generated by the LLMs, what do they do with them?
Okay, so they use these enhanced descriptions to train what they call a text-based representation. They use a technique called masked language modeling, or MLM.
MLM, like how models like BERT are trained.
Exactly like that. Think of it like this. The AI sees these detailed descriptions, but with some words randomly hidden or masked.
And it has to guess the missing words.
Precisely. It has to learn to fill in the blanks based on the surrounding text, the context. The underlying idea is that concepts with similar clinical meanings will end up having similar text-based representations.
Because they'd appear in similar descriptive sentences with similar words around them.
You got it. It's like a language model learning that car and automobile are very close in meaning because they tend to appear in similar contexts in text.
Okay, so that handles the meaning based on the text descriptions. But didn't you say there was more to it, something about connections?
Yes, precisely. They didn't stop there. The second layer of this concept representation learning involves incorporating the graph ontology of the OMP vocabulary.
Graph ontology. Sounds complex.
Imagine it as a massive map, or maybe a network, where all these medical concepts are nodes, and they're connected by lines based on established relationships.
What kind of relationships?
Things like is a type of, or is caused by, or is treated by. For instance, influenza might be linked to fever and cough as symptoms, and also linked to antiviral medication as a treatment.
Okay, like a knowledge graph for medicine.
Exactly. They used a framework called graph contrastive learning, specifically one called GRACE, to make the model understand these connections.
How does GRACE work, in simple terms?
Think of it like this. GRACE helps the AI learn that concepts which are closely related in the graph should also have similar representations. It contrasts related concepts with unrelated ones. So diseases that often occur together, or a condition and its common treatment, their representations get pulled closer together in the model's understanding.
So it learns the friendships or links between medical concepts, not just what they are individually.
Right. It refines those initial text-based representations by adding this layer of relational knowledge.
Now, this sounds really powerful, combining text, meaning, and relationships. But the researchers also flagged a potential issue, something called feature collapse.
Good question. Yeah, they were aware of that. The worry is that the graph learning part, while focusing on the connections, might start to overemphasize these links.
And lose the details.
Potentially, yes. It might lose some of the nuanced information it initially learned from those rich text-based descriptions generated by the LLMs. It's like focusing so much on who knows whom in a big group that you forget the individual personalities.
Okay, so how did they prevent that? How did they keep both kinds of knowledge?
They used a clever technique called learning without forgetting, or LWF.
Learning without forgetting. Sounds intuitive.
It is. Think of it as the AI trying not to forget what it already learned from the text descriptions while it's busy learning the new information about the graph connections.
How does it technically do that?
They use a mathematical measure called Kullback-Leibler divergence, KL divergence for short. You can think of it as a way for the model to constantly check back, how far am I drifting from my original understanding based on the text?
Like a tether back to the initial knowledge.
Exactly. It acts as a regularizer, ensuring the model retains that initial text-based knowledge while still effectively incorporating the valuable graph information, a stay true to yourself reminder for the model, if you will.
So the end result of all this, the LLM descriptions, the MLM training, the graph learning with GRACE, and the LWF is the final set of concept representations.
That's the output of this first big part, yes. And these representations are much richer than just the original concept IDs.
Because they capture both the textual meaning and the network relationships.
Precisely. The paper even suggests that these Pre-trained representations could potentially just replace the standard embedding layers in existing EHR foundation models.
Wow. Okay, so you could sort of plug these enhanced understandings into current AI models.
That's the potential, yeah. It sounds like a pretty significant step forward for making models understand concepts more deeply.
Definitely. Okay, that covers the concept representation learning. Now let's shift gears to the second main part of MedRep, trajectory augmentation.
Right. Trajectory augmentation.
First off, maybe just remind us, what exactly is a patient trajectory in this context?
Sure. Think of a patient trajectory simply as a chronological sequence of all the medical codes associated with a particular patient over time,
So their diagnoses, medications, procedures, lab results.
all laid out in the order they happen. It's like a medical timeline, their specific journey through the healthcare system documented using these OMOP codes.
Okay, so we've seen how MedRep teaches the AI a more robust understanding of the individual concepts. How does trajectory augmentation address the fact that these trajectories, these patient journeys, might look different across hospitals, even for similar patients, because of those different concept IDs, for instance?
Exactly, that's the link. So what MedRep does here is, for each medical concept within a patient's trajectory, it first figures out its closest neighbors, which other concepts are most similar.
Similar based on what? How often they appear together?
No, not based on co-occurrence. Similar based on those learned representations we just spent all that time discussing.
Based on the combined text meaning and graph relationship understanding.
Exactly. They use a standard mathematical measure, Euclidean distance, to calculate the similarity between the representations of different concepts. It's like finding the concepts that are closest in that rich, multifaceted meaning space the AI has learned.
Okay, so the AI identifies concepts that are semantically very similar, even if they have different ID numbers. What happens next in this trajectory augmentation process?
This is where the augmentation part comes in. It's about deliberately messing with the data a bit, in a smart way.
How so?
The system randomly selects some of the concepts within a given patient's trajectory and replaces them with one of their identified similar neighbors.
He swaps out a code for a very similar one.
Yes. The crucial thing here is that the replacement concept is semantically very close, meaning it represents roughly the same clinical idea, but it might have a different, previously unseen concept ID.
Especially if that neighbor ID is one that's more common in a different hospital's dataset.
Precisely. The whole point of this is to train the model to be more resilient, more adaptable to encountering these slightly different but essentially equivalent codes in the real world.
It's like showing a language model synonyms or different ways of phrasing the same idea.
That's a perfect analogy. You're training it to understand the underlying meaning, not just the superficial form, whether that's specific words or specific concept IDs. It makes the model more robust to the kind of variability it will definitely see across different institutions.
That makes a lot of sense.
Mm.
So the model gets exposed during training to variations it might encounter later, even if it hasn't seen those exact code sequences before. Now, the paper mentions augmentation factors. What do those tell us?
Right, the augmentation factor. It basically just controls how many of these replacements are made within a single patient's trajectory during training. Is it just one or two swaps or quite a few?
So they experimented with different levels of this swapping.
Yes, they tested different factors to find the sweet spot. You want enough augmentation to really improve how well the model generalizes to new, unseen data.
But not so much that you distort the original trajectory too much and hurt its performance on the data it was trained on.
Exactly. If the augmentation factor is too high, maybe the AI starts to get confused by too many synonyms being thrown in. It's a balancing act.
Okay, finding that optimal balance. Now, the big question. Let's talk about how well this actually worked in practice. They evaluated MedRep on several different sets of real-world data, didn't they?
They did, yes. They used 3 main data sets for evaluation. There was MIMC-PHI,
Which is a big, well-known public EHR database from the U.S.
right, widely used in research. Then they also used EHRSHOT, which is another open data set specifically designed for testing how well these kinds of foundational models perform on benchmark tasks.
Okay.
And importantly, they also included a private data set from Seoul National University Hospital, SNUH, in South Korea.
So data from a completely different country and healthcare system.
Exactly, which is crucial for testing real-world generalizability.
And the way they set up the testing is particularly relevant to our initial question about using AI across hospitals, right? How did that work?
Absolutely critical setup. They trained their baseline models, the existing methods they were comparing against, like standard BERT-based models, using only that MemiCorV dataset.
Okay, trained just on mimicking.
Then they tested all the models, including the ones enhanced with MedRep, on all three datasets. So on Mimicry itself, to check performance on familiar territory.
And crucially, on EHRSHOT and SNUH, the external datasets.
Yes. And the key point is, they did this without any additional training or fine-tuning on those external EHRSHOT and SNUH datasets.
So straight out of the box, how well do these models hold up when faced with completely new hospital data, potentially with different coding patterns?
That's the core test. It directly addresses that central problem we started with.
And they compared MedRep against some established models in this space.
Yeah, they use several baselines like Retain, which is an older but interpretable model, and more recent transformer-based ones like BERT, BERTday, and MedBERT. They also compared it against another concurrent method called MedTalk, which also tries to address vocabulary issues.
Okay, so what were the main results? Did MedRep make a difference?
The findings were really promising, actually. Across the board, the models that incorporated MedRep showed either better performance or at least maintained their performance compared to the baselines, especially on those challenging external data sets.
Maintained performance is good, improved is even better. What kind of tasks were they predicting?
They looked at several important clinical prediction tasks. Things like predicting in-hospital mortality, whether a patient would unfortunately pass away during their hospital stay.
Okay.
Also, predicting long length of stay, and predicting 30-day readmission, whether a patient would need to come back to the hospital soon after being discharged. Standard but important benchmarks.
And MedRep helped with these on the new datasets.
Yes, and interestingly, they found that MedRep consistently outperformed that other method, MedTalk, in both their internal tests on MIPV and, more importantly, on those critical external validation tests using EHRSHOT and SNUH.
So the models using MedRep were better at predicting these key patient outcomes, even when looking at data from completely different hospitals they'd never explicitly trained on before. That's pretty compelling.
It really is. And the paper specifically highlights how that trajectory augmentation step, the random swapping of similar concepts, really seemed to help make the models more consistent and robust in their predictions across the different data sets.
So that augmentation wasn't just a theoretical idea, it demonstrably helped bridge the gap.
It appears so. That's a key takeaway. It strengthens the model's ability to handle the natural variations in how medical information gets recorded in different places.
Did they do any tests to isolate the impact of the different parts of MedRep? Like, what if they only used the LLM descriptions or only the graph part?
Yes, they did. They conducted what are called ablation studies, where they essentially remove components one by one to see the impact.
And what did those show?
They found that basically you need the whole package for the best results. Using the richer concept descriptions from the LLMs, plus incorporating the graph information about relationships, and using the trajectory augmentation together gave them the best overall performance, particularly on the external validation.
So it's the combination of all these elements, understanding the concepts better and being robust to variations that makes MedRep effective.
It seems that way, yes. The whole is greater than the sum of its parts here.
And what about those different augmentation factors they experimented with? Did they find a level of swapping that seemed to work best generally?
They did look into that. Their experiment suggested that an augmentation factor of around 5, meaning replacing roughly 5 concepts in a trajectory on average, though it depends on trajectory length, often led to the best performance on those crucial external validation data sets.
While keeping performance on the original training data pretty stable.
Exactly, it hit that sweet spot. Introducing enough variation to boost generalizability without degrading the model's core knowledge too much.
Makes sense. Okay, this sounds very positive overall. But of course, no research is ever perfect. What did the authors themselves identify as limitations or areas for future work?
They were quite upfront about a few things. Firstly, they mentioned the computational resources required. Generating these enhanced representations for all 9 million plus concepts in the full OMA vocabulary is a huge task.
Yeah, so they didn't do it for every single concept?
Not yet. For this paper, they focused on a subset of around 1.8 million concepts, the ones most frequently appearing in their datasets. But they did state they plan to eventually compute and release the full set of representations.
Which would be a massive resource for the community.
Absolutely. A huge contribution if they do. Secondly, they pointed out that the observation table in the OMP CDM standard wasn't used in this study.
What kind of data is in the observation table?
It often contains less structured data. things like social history, lifestyle factors, maybe some notes snippets data that doesn't neatly fit into the condition, drug, procedure, or measurement categories. Integrating these diverse data types is definitely an important area for future work.
Yeah, bringing in that richer, sometimes messier patient context.
Right. And finally, they suggested that exploring more sophisticated trajectory augmentation techniques could be beneficial.
Beyond just randomly swapping concepts with their nearest neighbor.
Yeah, perhaps techniques that consider the context within the trajectory more, or different ways to introduce plausible variations. There's likely room for improvement there too.
Okay, so limitations acknowledged, but the core approach seems solid. What's the main thing our listeners should take away from this deep dive into MedRep?
I think the key takeaway is that MedRep offers a really promising approach to building these big EHR foundation models, so they're much more adaptable, much more generalizable.
Less brittle when they encounter data from a new hospital.
Exactly. They're less likely to be thrown off by the unavoidable differences in medical coding practices we see across different healthcare systems, even those that are supposedly using the same OMOP CDM standard.
Which really moves us closer to a future where powerful medical AI tools can actually be deployed more reliably, more widely.
Yes, in a wider variety of healthcare settings,
So,
which ultimately has the potential to improve healthcare equity and outcomes for everyone, not just patients in the specific hospitals where the models were originally trained.
absolutely. And this makes you think, doesn't it? What are the broader implications here if we can get better at sharing insights from medical data across populations?
What does that mean for personalized medicine? Could we tailor treatments better by learning from a much wider, more diverse pool of patient experiences?
That's a fascinating question. And it also makes you wonder, what other challenges are still out there? Beyond this vocabulary issue, what else do we need to solve to truly unlock the potential of shared medical AI knowledge?
Definitely lots to ponder there. Big hurdles remain around privacy, data access, bias.
Yeah,
It's complex.
for sure. Now, for those listeners who are really keen and want to dig into the nitty-gritty technical details of MedRep,
Good news there. The researchers have made their paper, and, importantly, the code they used publicly available. It's up on GitHub.
excellent. We'll make sure to include a link to that repository in the show notes for anyone interested in exploring their methods and maybe even trying it out themselves.
Yeah, it's a fantastic resource for transparency and reproducibility.
It really is. This whole area just highlights the ongoing journey, doesn't it? Trying to make sense of incredibly complex medical data to actually improve people's health.
And it's genuinely exciting to see innovative approaches like MedRep emerging, techniques that offer practical ways to start bridging the gaps between these different silos of medical knowledge. It feels like real progress.